So, so we're in unit 2, and we're focusing on addition and subtraction now, but that could mean so many things, right? So that's weird. I don't know why these investigations are here. Course resources. Eventually. And then we go to blank notes and completed notes, right? So the blank notes are where you get the individual files. All right, we're looking at 3.1 to 3.5 right now, all right? So that's what you'd want to open up. The other possibility is that you just live in the completed notes, which also has the 3.1 to 3.5 included, right? The difference is that this has the, this will have completion, right? So the, after we take notes, we will have, this one will be all marked up, but the other one won't be, all right? So it all depends on what you want. So let me stop that share. And I'll go to iPhone, iPad. Apparently I gotta install a plugin because, why wouldn't I? And bring up the file. So we're in the realm of interpretation now, all right, at least to some extent. All right, so we're talking about addition, subtraction exclusively in this unit, but addition and subtraction of what? We're talking about adding and subtracting fractions, decimals, whole numbers, integers, things like that. All right. So a little blurb here. The most basic way to interpret addition is as adding to, and the most basic way to interpret subtraction is as taking from. But we also use addition and subtraction to solve problems that arise in put together and take apart situations, but also in compare situations. All right. So the most familiar ways to think of addition and subtraction are as combining and taking away. But as we'll see, there are a surprising variety of types of types in which we add or subtract. So there's a nice typo for somebody. It's right. It's really types of problems in which we add or subtract. Yeah, that's probably the better adjustment. A little types of problems in which we add or subtract. All right, so a quick example. Let A and B be non-negative numbers. We can define A plus B as the total number of units of the combined sets A and B. So good luck explaining that to a kid and using those words, We could also think, oh, geez, this is all over the place. It's crazy. Think of the sum. Well, it's bonus points for somebody, so that's all I care about. Think of the sum as the total distance traveled along a number line. All right. So when I find the sum of A and B, if A is 12 and B is 15, I want to make use of that number line. Right? So that's not too bad. What I would first do is plot the location of A. And then from there, I would travel an additional. This is getting brutal. Justify your answer. Travel additional 15 units to get to my total, right? But I'm using the word travel strategically here, right? That's actually what you're doing. You've already traveled 12 units, right? So that's this distance. Now I'm going to go 15 more. So you're counting little tick marks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so that gets me to location B. All right. well, it's really B more, right? So I'm just going to go, that's a total of 15. Or it will be a total in a second. It's a 15 unit movement. But what I want is the sum total of all of them. So what I would do is I would count off from 0, right? So I'd be looking at starting at 0. I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, all the way up to 27. So this distance here is a total of 27. All right. So this first piece is a unit, or well, it's 8 units, but specifically 12 units. And let me just move this and bring it back in a sec. Put it underneath. And then this guy is the 15. All right. I think that's a little bit better than the squigglies, which I'm going to get rid of in a sec. Yeah, a little bit nicer that way. So that gets you to a total of 27. Right? So we're looking at, in the grand scheme of things, A plus B is going to be equal to 27. All right. So again, as you discovered on the last skills assessment, we're not dealing with you just demonstrating that you can add 2 numbers together. All right. You're going to have to explain to me how you would explain to a small child that you're using a number line, that 12 plus 15 is equal to 27. All right. So this idea of counting off 12 units and then counting off an additional 15 units, that's going to be pretty important. All right. So it isn't like, no offense, I'm not impressed by you demonstrating that you can just simply add 12 and 15 together. All right. That's great. I mean, slash, that's like, yeah, you better be able to do that. Right. You need to be able to show me how you would explain to a young one that the sum is actually 27. That's a different animal altogether. All right. Now subtraction is a special form of addition. All right. So it's tricky for students because the act of subtracting, you know, brings up other concepts, because what you're dealing with are instances where, you know, it's like, what happens if I have 20 of something and I want to take away 40 from that something? For a young one to conceptualize that could be pretty daunting, you know. So we have to kind of delve into this idea of subtraction and addition as movements along a number line, or dive into that idea, because if we don't do that, then it just becomes this vague concept that's just floating around in their minds, right? And it never really kind of latches onto any true understanding. So that's why, you know, back in the day when teachers would say, "Don't use your fingers. Tell me the sum without using your fingers." It's like, yeah, that's down the line. Early on, the concept of using fingers to come up with addition and subtraction, that's actually a great strategy. Because if I want to have a total of 7, for example, I'm starting off with 3 and I'm adding 4, I would count off 1, 2, 3. That's like 3 tick marks on a number line. And then I want 4 more. So 4, 5, 6, 7. I would get to my result. It's the same idea as counting along a number line, right? So it went from don't count on a number line, don't count with your fingers, to let's count on a number line. But then it's like, well, isn't that the same as counting on your fingers? And the answer is yes, right? So pretty hypocritical, but you know, that's how education works. You know, we decide something is not a good technique, and then later on we realize, oh, wait a minute, probably is. You know, addition and subtraction can be thought of right, as yielding a quantity, but it could also give a position. right? Emphasizing both meanings allows students to more quickly capture the true meaning of addition and subtraction, right? So a couple of examples. Timmy bought 7 tacos to bring to a play date with some of his friends. When he arrived at the play date, he saw that only 4 of his friends were there, which means he bought, I guess it works in this case, too many tacos. How many extra tacos will he have? All right. So what you could do, I mean, I suppose you could just say 7 minus 4, and that's the end of it. But that's not getting at the underlying concept, right? So the better way of handling it, whether it's through a number line or a diagram of some kind, is a visual approach, right? So I don't know that you need to actually draw tacos, but what you could do is use points to represent the tacos, right? So I'm going to let these be my tacos. And this goes hand in hand with the bears thing that I was doing with that Desmos. So each one of these dots represents a taco. Now we have friends. All right. So we want to know how many extra tacos will he have? Well, he's only got 4 friends there. So each one of those friends is going to get a taco. And, you know, there's an underlying assumption here. And sometimes you want to spell that out for the students. But the underlying assumption here is that they're only getting 1 each in order to keep it fair. Right? So what I would do, using my technology, is I would move a taco into the box representing just the stomach of a friend. I don't know. You know, I'm just grabbing them at random here. And so once I've moved those tacos into the possession of the friend, then I know how many are left over, right? So then we could say that there are 3 tacos left. So I'll say 3 extra tacos just to use the language of the question. Right. So you can do it that way. That's a pretty solid approach. You know what I'll do though is I'll bring the points back and I'll just highlight them. All right. So I have my 3 extra tacos. The ones that got moved, you know, say these 4, for example. Now, the follow-up there, how did we know that the best way to tackle the problem above, or the above problem, was through subtraction? Well, I don't know. Maybe you didn't recognize that it was subtraction. All we did was we moved from one group to another. All right. So, you know, using language, we can kind of get to that idea. We reduced the number of tacos by giving 1 to each friend. All right. Reducing, giving implies subtraction. All right. So they're key words. Key words for subtraction. All right, so we reduced the number of tacos by giving one to each friend. So I took away from my collection of tacos. Now the friends each gained a taco, so that for them it would be addition. Like if I were one of the friends, I would start off with 0 tacos. I would now have 1. How could I get that? I could say 0 plus 1. But from the pool of 7 tacos, a total of 4 were removed, and now Timmy only has 3 tacos left over. All right. Now I would imagine that one of them is for himself. So, there is a little bit of gray area here because you could look at it and say, well, does he really have 3 left over? Well, he's probably going to eat 1. So maybe he only has 2 left over, but based on the construct of the question, we're going to assume that it's just the raw question. He's distributed them all. How many does he have left? All right. So another example, Timmy bought 7 tacos to bring to play date with some of his friends. When he arrived at the play date, he saw that 10 of his friends were there, which means he did not buy enough tacos. How many additional tacos should he have bought? Justify your answer with a number line, right? But before I do the number line thing, what I'm going to do is come up with my pool of tacos again, and my friends, or Timmy's friends. We got 7 tacos. And I might as well just draw the boxes again. Struggling. There we go. Probably don't need them to be so big. There we go. All right, so it's going to be generally the same idea, where what I'm going to do is I'm going to start allocating tacos to friends. I can line them up if I want. Makes it a little bit more visual, a little bit more understandable. So then I could say, all right, this one's going here, one's going there, 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 and finally there. So I have a taco for you, I got 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 a taco for you. Oh no, I don't got a taco for you. All right, so these, no tacos. All right. So they didn't get any tacos, which means I'm short 3 tacos. All right. So Timmy should have bought 3 more tacos. All right. So he's short 3 tacos. Now, if I apply this computation here, I could be looking at, for example, 7 minus 10 gives a result of -3. All right. I could also look at it the other way and say that I'm taking the 10 people that I have, subtracting from that the 7 people who are getting tacos to see what's left over. But here, the follow-up question is saying, what's the significance of a negative number in this case? So we'll have to get onto that, right? But the way we could look at this if I create a number line, let me start it at 0. That's crooked. Still not. Yeah, whatever. Just dealing with it. So I'll plot 0. Okay, not good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll get rid of the extra. All right. So we can look at it this way and say, all right, well, I have 10 people, 10 available slots. So what I could say is 7 of them are accounted for with tacos. All right, that gets me to the 7 mark. And so that gives us a remainder of 3, a 3 left over. So you can look at it that way. That's one number line justification. Another way of doing it would be to say that you're somehow reducing the number of tacos by the number of required tacos. Right? That could be a little bit trickier for kids to understand, but that would get the job done. Where you would say, all right, I got my 7 steps in the direction of tacos. Right? So positive tacos, that gets me over to this location. But then I take 10 steps the other way because those are the tacos that I need. All right, so have versus need. Positive would be the have direction, negative would be the need direction. So let me show you what that number line would look like. It's really more like just movement, right? So the negative numbers would be the need, and the positive numbers would be the have. Right, so what I would do is I'd start off at 0, and I'd say, okay, I'm taking 7 steps in the direction of have. Right, so 1, 2, 3, 4, 5, 6, 7 steps. All right, so I've gained 7 tacos, but then I could go the other way and say, but I need 10 of them. So I would take 10 steps in the other direction by saying 1, 2, I need 10. So 3, 4, 5, 6, 7, 8, 9, 10. All right, and that would get me to -3. So after I make the 7-step movement in the positive direction, I would follow that up with a 10-step movement in the negative direction. All right, and that equates to the idea of subtraction because it's 7 plus -10 is the same as saying 7 minus 10. Just going to reduce the size here a little bit. Just clean it up a little bit. All right. So the significance of a negative number in this case, I would like to think that it's pretty obvious. It's kind of like money, where it's amount owed. Right. So the amount of tacos that we're short by. All right. Now it is entirely possible that you could do all this stuff without ever dealing with a negative number, right? But you want to hit on the different modes of instruction. Again, the computational, the visual, right, and the verbal, right? So here we got it all. We did a 7 minus 10, which is -3, computational. Right? We got visual. We got visual up the wazoo. We got the diagrams involving tacos and friends, 3 different types. And then we got the verbal, where we have a verbal description, a written description of what we're talking about. So those are the 3 modes, right? If you're wondering, expositional is not a mode of instruction in math, right? Just Google what exposition means and you'll see, right, if you didn't know, right? So don't be surprised if that question comes up again on the next skills assessment. Oh, actually, let me be clear about this. That's coming up on every single assessment the rest of the way, all right? I am gonna ask what the 3 modes of mathematical instruction are on every assessment. So the second test, the third test, and the final. All right, all those skills assessments, they're all going to ask you the same thing. All right, among other things, but that question will be on there. All right, so definitely get to know that one. That's how important it is. All right. So next page, we'll tackle some putting together and taking apart problems, and then a couple of word problems, and then that'll be it for tonight. All right. When you're dealing with different strategies for addition, subtraction, we have the counting on, the take from 10, and the displacement strategies. We've actually already tackled displacement, because that's the number line. But the counting on, that's kind of along the same idea, or the same lines, because the counting on and displacement sort of go hand in hand. It's basically saying, all right, I'm starting at 1 when I'm counting on. I'm starting at 1. I'm gaining 5 more, and then I'm gaining 9 more upon that, right? So now I'll just start it off at 0, because it's all positive. So here's 0. If I'm counting on, what I would do is I would establish the location of 1. Well, 1 right here. So I'm going to tack on another 5. But what I would want to do is just simply count on 5 more values, right? So 1, 2, 3, 4, 5 more values. So that gets me up to 6, right? And then I would want to count an additional 9 values. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So very simple. Gets us up to a total of 15. It would take a minor miracle for me to fit the number 15 in that tiny box that I created. So that's another typo for somebody. I'll just write it next to it. Well, yeah. Right, but the problem below it amounts to the same thing. It's exactly the same thing, except your work is going to look a little different. Right? So don't be surprised if this concept comes up on a skills assessment, because this is my way of knowing that you know the appropriate strategies, because I know you know how to add 5 plus 9 plus 1. That's not the question. That's not the concern. Can you teach the appropriate strategies to the next generation, if you will? Right? So here I'm plotting 5. Starting off at 0, then I'm going 9 more. That gets me to 14, and then I do the 1 more upon that, which gets me to the 15. So it's the same answer as expected, but you can see the justifying work, or the supporting work, looks vastly different. Right? There's 2 different number lines that support the same answer, right? And that's because what we're dealing with here is an example of the commutative property. Right? Whenever you reverse the order of numerical values in addition or multiplication, you're applying the commutative property. All right. Now, another technique would be to build to or take from 10. So the way we handle that, we tackled this a little bit. I think it was the first class, maybe the second class. What we do is we think of 6 and 7 as a collection of items. All right, so 6 seashells and 7 more seashells. All right, so what we do, and I'll do it numerically and I'll also do it using a diagram. So if I look at the 6 and the 7, I could do it one of two ways. I could say, right, the 6 is 6. The 7 could be split up into two values. One of those values, as a sum, one of those values should serve to make that 6 into a 10. All right. So I'm thinking about how I can get to the number 10 from 6. I would need 4 in order to do that. So I could think of 7 as the sum of 4 and 3. So what I would then do, because it's still true, 6 plus 4 plus 3 is the same as 6 plus 7, right? But what I can do is I can look at this. See, I got this combo here. Add them together. It's really 6 plus 4. Then I have the plus 3 off at the end, right? So I'm using my properties to my advantage. I'm able to say, all right, that's 6 plus 4 there is really 10. 10 plus 3, much easier computation. Not to say 6 plus 7 was overwhelmingly difficult, but in the mind of a young one, yeah. So this is much easier. 10, 3 upon the 10 is going to get me to a 13. All right. So all you're doing is you're finding groupings of 10 from the numbers that you have available to you. Another way to do it is a diagram approach. That could get a little crazy if the numbers get big, but if I take the number 6, for example, I can write it as 1, 2, 3, 4, 5, 6. The number 7, 1, 2, 3, 4, 5, 6, 7. Then I'd be looking at it and saying, okay, well, I got a total of 6 here. To get to 10, I would need 4 more. And then I would just cluster up the remaining values. All right, so I'd have 10, 3 gives a result of 13. All right, the drawback, there's a couple of drawbacks to this approach. If you do it this way, it kind of begs the question, well, why not just count the dots? If you've already plotted the dots, you probably already know how many there are in total. So this is more of a justification for why your answer is really equal to 13. I don't think there's too many people that are ever going to intentionally use this technique in order to arrive at the answer to begin with. It's more like a justification, right? But then we could also go from with the perspective of taking from 10, right? Or build to or take from 10. It can get a little dicey for kids though. They don't always like this technique because they want to be able to count with their fingers and just call it a day, right? Or they want to be able to just say, well, I just know it. Why do I have to do all this work? And it's a justification, right? You're justifying your answer. Now, this is essentially subtraction, but we want to be thinking about how I can get to, if I'm gonna build to a value of 10, I want to be thinking about how I can get there, right? So what I'd be looking at is a couple of strategies. One is actually a little bit easier than the other. And in fact, you kind of look at this and say, well, what, and you'd be justified in thinking it. Why not just do this? If 9 is comprised of 6 and something else, why not say 6 and that's something else? And my answer to that is, well, that's what the question is. If I'm looking for a justification, that's not going to get the job done. All right. So what I would do instead is build the right-hand side up to equal 10 and then see where that takes me. All right. So I know that 6 plus 4 is going to give me a 10. All right. So I'm going to add 4 to this side. All right. So 6 plus 4 will give me a 10. So I'm getting to the closest round number. Now, round number specifically 10. It turns out the closest one near that 9. All right. So what we get is a logical progression here where I would say, okay, I added 4. And the result was 1 more than what I wanted. All right. So then that would tell us that the answer ought to be 3. All right. So the idea behind this isn't so much that you're using this combinations to get to 10 in order to get an answer. It's more like you're trying to force them into logical reasoning. You get to a point where you say, all right, well, what was your thinking behind that? Well, I started off with this and I added this many more, and that got me there. But if you force them to build to or take from 10, then what you're doing is you're saying, okay, we got to a 10. Now how does 10 relate to that 9? 10 is 1 more than 9. So I added 1 more number than what I should have added, right? So I added 4 to the 6. It got me 1 more than what I wanted. Hey, that's just like counting with your fingers and overshooting it, right? So if I'm saying, okay, I want to count to 9, so I start off at 6, 7, 8, 9, 10. Oh, I went too far, right? So let me just go back 1. I only needed to count off 3 instead of counting off 4, right? So that's another application of it. It's really the logical reasoning component, all right? And we're not going to get to the word problems today because I'm looking at the clock. We'll just do the displacement one, and then that'll be it. Displacement is, I think, the most user-friendly one, except a second grader, first or second grader, is not going to know what the word displacement means. So you'll have to define that for them if you plan on using that word. Okay, but it's still a good strategy, right? So the question here, the main focus of the question is kind of like the count on approach, where I'm saying, all right, 6 plus something is going to get me to a 4. Well, we're going to figure out what that something is. So what I would do is say, all right, 1, 2, 3, 4, 5, 6. All right, so that accounts for this guy. So that's 6 steps in the positive direction. Six steps in the positive direction. So I need to ultimately end up with a 4, which is right here. That's my goal. So in order to get there, I have to go backwards. And you could start just counting boxes or tick marks. Starting at the 6, I'd have to go 1, 2. So I would need to go 2 steps in the negative direction. All right, so that movement, if it's in the negative direction, corresponds to a -2. All right, so what I'm doing here is I'm creating subtraction, and this is really the goal of this whole lesson. We got there eventually, but that's the whole idea. We're thinking of subtraction as a negative movement, right? So what this ends up giving me, and I'll just kind of use a red arrow here. Nah, I'll keep it as purple. This number is your value. It's really the same as saying 6 minus 2 is 4. Now, we knew that. We knew 6 minus 2 is equal to 4. But what this is telling me or giving me is the real justification for why we sometimes say 6 plus -2 instead of 6 minus 2. You say, oh, I say 6 plus -2. Couldn't you just say 6 minus 2? Yeah, you could, but then you lose a little bit of the meaning, right? So 6 plus -2, we know that that's the same as 6 minus 2, but this gives us a justification for why we would even consider writing the 6 plus -2, right? Because it's talking about movement, right? So 6 minus 7, so that's the idea here. If we're doing it as displacement, I don't want to think of it like that. I want to think of it as 6 plus -7. Right, so on a number line, what I'd be looking at, again, this time I need some negative values. I'll put a 0 here. 0. 1, 2, 3, 4, 5, 6. All right, so 6 movements in the positive direction, same as before, but now 7 units in the negative direction. So that's going to put me right here, 1 tick mark to the left of 0. All right, total of 7 movements. Use a highlighter here. And that's where we could get the -1. But again, it has everything to do with the displacement, the movement. Right? We're taking 6 steps in the positive direction. So this is a +6. We're taking 7 steps in the negative direction. And that gives us a final result of -1. All right. So that's going to do it for tonight. I'm going to stop the recording.